Hi everyone. Today I will try to explain the concept of instruction level parallelism or ILP. In this tutorial, you will get a brief overview of instruction level parallelism, then how the concept of ILP has been implemented in computer architecture. So if you go back to the concept of general pipelining, in pipelining, what usually is being done, pipelining can overlap the execution of instructions when they are independent of one another. If you can recall the concepts of arithmetic pipelining or instruction pipelining, you can figure out that at those places the basic assumption was that the instructions are independent of one another. While the instructions were not independent of one another, what usually happened, you had different types of problems, say data dependency, branch difficulty, and so on. But instruction level parallelism tries to explore the potential parallelism or potential parallel execution in instruction level. The potential overlap among instructions is called instruction level parallelism when the instructions can be evaluated in parallel. So to understand this, let me create a hypothetical situation, and it says that imagine an educational institution's admission section operates with three functional units: reception, certificate verification, and fee remittance. So let me try to implement this in a block diagram. So there are three functional units: reception, then we had uh, certificate verification, then we had fee deposit. So these are the three functional units. Now imagine that some candidates are queuing up and waiting for their turn. Candidate 1, candidate 2, candidate 3, candidate 4, candidate 5, candidate 6. So if you try to find the analogy of this situation with simple pipelining or general pipelining, there is one functional unit for the reception. That means at a particular time instance, only one candidate can be received at reception. While, so how this will happen, say at time instance T1, candidate C1 receive at reception desk. Now once the reception task is complete, Then at clock cycle T2, candidate C1 will be passed for certificate verification and candidate C2 is received at the reception. So, what is the takeaway? At a particular time slot, at a particular segment, only one instruction or one candidate can be entertained at a particular CPU segment. This was the concept of um, simple parallelism, simple pipelining in SISD architecture. Now, how we can take advantage of instruction level parallelism to achieve more speed up? If you carefully observe these candidates, the 6 candidates, they are independent of one another, and that is the key observation. So our key observation is the candidates which are in our example C1 to C6 are independent of one another. There are no interdependencies among them. So, what we can do with little cost, we can add some extra bit of hardware. Say, now at reception desk we employ 2 persons, R1 and R2. At certificate verification stage also, we employ 2 persons, C1 and C2. At fee deposit desk, we employ 2 persons, F1 and F2. Now this R1, R2, C1, C2 and F1, F2 will act as different functional units. Although R1 and R2 will perform the same category of task, but their task will not overlap with one another. Why? Because the instructions or candidates we are going to supply them are independent of one another. Now just observe how speed up can be achieved here. Sorry, just wait a moment. Say now at time cycle T1, what happens? You can assign candidate C1 to R1 and candidate C2 to R2. So you can see that same tasks for 2 different candidates are being done parallelly at the same clock cycle. Now at clock cycle T2, what will happen? Both the candidates C1 and C2 will be handed over to certificate verification desk together. So candidate C1 will be assigned to certificate verification person C1 and candidate C2 will be assigned to certificate verification person C2. One thing you should take care of is that this C1 and this C1 are different actually. This C1 is a certificate verification personality and this C1 is a candidate. So by adding an extra bit of hardware to a particular stage, we are increasing the level of parallelism, and this parallelism is achieved by observing the nature of instruction or nature of the candidates arriving. So this is called instruction level parallelism. Now try to replicate this analogy to computational domain. For this, let me write a bit of program code. We will write a simple for loop for int I equals to say 0, I less than 100, I plus plus. This is a simple for loop which is common to every programming language. A I equals to bi plus ci. Okay. Now, if you carefully look into this for loop, this is basically an arithmetic operation, right? Basically, what is being done? The value of bi and ci added together and is being stored into a third variable called ai. Now, when you write down a program, this is basically a single statement. But when you execute this, what happens? It is basically not a single statement. Rather, there are 100 statements being embedded into a single statement. How? Basically, what this for loop is doing is a0 equals to b0 plus c0. Then in the next iteration, a1 will be computed, b1 plus c1 a2 equals to b2 plus c2, and the same operation will be done up to a99 equals to b99 plus c99. So what is the takeaway? Basically, in a single statement or single arithmetic operation statement, 100 arithmetic operations are being done. Now, the point to observe in this scenario is, if you look into the individual operations, you can find that a0, the operation for a0 is independent of operation for a1. Operation for a2 is independent of operation for a1 and a0, as well as the following operations, a3. So, if you can replicate the concept of this analogy to this simple instruction, you will obviously achieve some extra degree of parallelism. Now, how this can be achieved? Say, now your instruction pipelining has instruction fetch. For instruction fetch, you have two segments. Instruction fetch 1, instruction fetch 2. Now, say for instruction decode again, you have two segments, instruction decode 1 and instruction decode 2. And if this is your instruction 1 and this is your instruction 2, if you follow the previous analogy, now at clock cycle T1 you can actually fetch two instructions at the same time into the processor without any conflict. Instruction 1, that is the instruction to compute A0 equals to B0 plus C0, is fetched into IF1 segment of instruction fetch segment, and instruction 2 is fetched into IF2 segment of instructions fetch segment in the same clock cycle in our hypothetical processor. This is our hypothetical processor. So, hope if you have followed the discussion up to this point, you grabbed some concept of instruction level parallelism, how following the nature of the instruction, you can increase the degree of parallelism. So, your task will be to go through this definition and next go through these examples and do some brainstorming with these examples. Then you will surely get a sound concept of instruction level parallelism. The next concept is which is closely tied to instruction level parallelism is loop unrolling. If you go back to our hypothetical processor example, actually this is your for loop. What you actually did is you actually unrolled the loop, right? In loop, the statement was implicit. Implicitly, it was indicating that 100 addition operations are there, and for the purpose of implementation into the processor, what you did, you actually unrolled or explicitly expressed the contents of the loop. This is the base assumption behind loop unrolling. Just look into this example. This is a simple C statement, int main. Then inside int main there is a for loop for int I equals to 0, I less than 5, I plus plus, then printf hello. So what this for loop will do? This for loop will actually print this line hello for 5 times. So this simple set of C statements can be written in another way also. How? Come to the next program, program 2. In program 2, what we have done, we have written the printf 5 times. If you follow the output of both the programs, you can surely say that the output is same for both the programs. So in the first version, the expression was implicit, the output was implicit, and in the second version, the statements were explicitly written, and the version inside the loop has been unrolled into the second version. So this was the concept behind loop unrolling, and this concept is being implemented using instruction level parallelism. So this was the theoretical background behind ILP. Now in the next video we will study how to implement this ILP concept at architectural level. Basically we have three suggestions to implement this ILP at architectural level. One is super pipelined architecture. Then next one is uh, super scalar architecture, and another one is very long instruction word or VLIW architecture. So go to the next video. There I will give some brief overview of these architectures.